I was born at the tail end of World War II. So a lot of things were rationed at that time. But I did manage to get a bicycle, and I would take the bicycle apart. I thought you had to grease all of the bearings and everything at least once a week. So I'd take them apart and put them back together, take them apart, put them back together. I like to make model airplanes. So they had little kits to where you could cut them out and glue them together, you know, and then cover them and go fly them with a big rubber band on a propeller. You know, you just wind that rubber band up and then go fly for a few feet. So yeah, I did have an interest early on. Then coming through high school, I went to a county high school and did not have as good a foundation for college as I would like to have had. But somehow, some way, I did manage to graduate from Georgia Tech with a nice degree. And so that led right into me being able to come into the space program. I graduated in '57 and went to work in Decatur, which is 20 miles from here. My degree was in industrial engineering, so I went into an industrial plant. But then, you know, by '61, I kept hearing about what was going on in Huntsville. And I would say that the German team was putting out this data that we're going to the moon. And, you know, that just really intrigued me. So I told my wife, I said, I don't know what they're doing, but I'm gonna go over and find out. So I came over, I contacted the personnel office. Back then it wasn't HR, it was personnel. So I contacted them and I said, I'd like to come for an interview. And they said, well, we open at 6 o'clock. Can you come to Marshall or the Redstone Arsenal at 6 o'clock Monday morning? I said, I'll be there. So I came here, sat and talked. At 8 o'clock, I was on my way back to Decatur to turn in my 2-week resignation there so that I could come to work for NASA. So it was just that quick, and it was just such a wonderful environment for the space program early on. The camaraderie between all of the teammates here, just fantastic, just superb. From one fabrication environment to another, we were making rockets in the buildings right here on Redstone Arsenal. So I was assigned into that laboratory that was making the rockets. So you know. Now we bought the engines from Rocketdyne, so they were a deliverable unit, but then the rockets, the engines would be installed into the aft end of the rockets. So I worked here at Marshall up until the Space Shuttle, and I was ready to make a change, and they were looking in the Space Shuttle main engine. I'll be referring to it as the SSME, Space Shuttle main engine. They were looking for somebody to go to California because we had a resident management office in that plant in the Los Angeles area. So that's how I got involved with the Space Shuttle main engine I went to California in 1974, but let me back up to say Rocketdyne first revealed their design of the Space Shuttle main engine in 1970. So in 1971 then, they got a contract from Marshall Space Flight Center for $442 million to build the most complex, the most powerful engine system that had ever been built in the United States history. So that's how I got into this picture. So following in the 72 contract, in 73 and 74, they were making components that go onto that engine that were ready to be tested. So whenever I got to Rocketdyne in 74, that's the environment I went into, is we were making lots of hardware in the shop areas, and we had lots of testing that was going on. The testing was conducted outside of the LA basin, up in the mountains, The area was called Santa Susana. And so we would take our hardware up there and test the components there in the test stands. Okay? And then in 1975, Rocketdyne delivered its first engine, full engine, to NASA Marshall Space Flight Center in 1975. So that took 5 years from their revealing their design to delivering their first engine. So it is a horribly complex, but a mighty powerful engine. I've been a very lucky dude. I've been very, very fortunate. Absolutely. And it's been a wonderful life. The challenges that I helped to experience, and maybe I helped a little bit to provide solutions, has been so rewarding that it just doesn't get any better. Doesn't get any better. The Space Shuttle main engine is a reusable engine. It weighs 6,700 pounds. It has 470,000 pounds of thrust. It has a computer, we call it a controller. All three engines are gimbal, they gimbal. So that's just some of the things that goes into that. The whole SSME system was designed such that we could replace components in the field. So after a test, if you had something that appeared to have some indication of a problem from all of the sensors that we had on that piece of hardware, then we could pull that component out like a turbo pump, insert another turbo pump. We call it LRU, line replaceable unit. But this is the first time that an engine had been designed such that those kind of things can happen. It was very efficient. You did not have to recalibrate the entire engine because you had a highly qualified part, hopefully sitting on the shelf ready to be inserted. And that's the way the program was run. Very successful. So again, I went to California in 1974, and we had a resident management office there. It was a miniature snapshot of Huntsville's Marshall Space Flight Center. So we had some 15 or 20 people that were assigned there, but we covered all of the major categories of monitoring Rocketdyne, of how they were performing, how were they managing, how were their finances, et cetera. So we had contracts people there, we had finance people there, we had quality people there, we had engineers that came out of an organization or a laboratory here in Huntsville, and they were assigned to Huntsville for, again, a period of time. And so we had basically the techniques and the knowledge of all of our home base organizations or laboratories right here in Marshall, but we functioned daily out there. Okay. The way Rocketdyne had a management scheme that was very effective, and it was every morning at 7 o'clock. We had a stand-up meeting. What does stand-up mean? It means you go into an office area where there are no seats, no tables. All you had is wall space. And every critical component for that engine had a person there briefing what's the status of your hardware in the shops, in test, in repairs, if you've had an incident, the investigation that is coming along. All of that was very effective. So we got an update every morning And our resident management office staff participated in that to gain our data, and then we'd feed it back to Huntsville. Lots of times it'd result in travel of some people, further experts from the laboratories here to come out and participate. So travel arrangements were pretty high between Huntsville and California at that point in time. Well, the challenge was tremendous. If you looked at climbing a mountain, this one was almost straight up, because the design and build of the SSME, we were right on the ragged edge of technology and honestly of all engineers knew how to do. So we were that close to disaster every time we hit the button to ignite the system. So the challenges were very great. The responsibility was a corollary to that, because if you were working on that particular part and it failed, then you felt a personal responsibility for, where did I not do my job? What did I not think about? What did Rocketdyne not think about? So that was the relationship that we had with Rocketdyne. Very, very strong relationship. And that started at the program managers. J.R. Thompson was the program manager for the SSME here in Huntsville. Dom Sanchini was the manager for the program at Rocketdyne. They were friends, they were buddies, but they were strong engineers, and they had a huge responsibility to meet the schedules that had been laid out within the dollar amounts that was planned. Well, let me say that at Rocketdyne, in the 60s, they were running about 4,000 employees. In the 70s, we were up to the 10,000 employees. So we had highly qualified machinists, welders, every kind of skill that you need in a shop environment to build something. We had it right there at Rocketdyne. So we were operating 6 and 7 days a week, 24 hours a day. So we had all 3 shifts. I know in our resident office, we would come in and catch sort of the tail end of the 3rd shift that came out at 7 o'clock. We'd stay through our shift, 1st shift, and then we'd stay over a little while into the 2nd shift. So we got to see and learn a lot of the guys in the shop areas. Again, it was a team, absolutely a team effort. So you couldn't ask for any better qualifications of staffing, commitment. A lot of them, had not taken vacations in quite some time because they were committed to the program in the shop area. So this was really encouraging, and it was contagious. So there was a lot of pressure, particularly when you had an incident and you had to shut down your test sequencing until you got some additional hardware, because you didn't make these components overnight. So. Well, let's start at the external tank, because that was where our fuel was stored. The external tank was nothing but huge 2 tanks, a liquid oxygen and a liquid hydrogen tank. I may have to refer to some of my numbers because they are so big, but the liquid hydrogen tank had 383 gallons of hydrogen in it. On liquid oxygen, they had 134,000 gallons. Now we had 17-inch diameter lines that fed from that external tank to our Space Shuttle main engine. So the flow there was much higher for the hydrogen than it was for the liquid oxygen. But, well, let me look right here just a second, because it's sort of mind-boggling how many gallons was pushed through those, there it is. The liquid oxygen flowed at 17,000 gallons per minute through that 17-inch line. When the pump, whenever the flow was called on, it came to our low pressure pumps. We had a low pressure oxidizer pump and a low pressure hydrogen pump. So they would come to those pumps and sit at valves ready to come right into our system. The low pressure oxidizer pumps it spun at or pumped at 5,000 revolutions per minute, and it raised a rated horsepower of 1,600 horsepower. Whenever that low pressure pump was given the green light to ignite. Okay. So let me go then to the low pressure pump on the hydrogen side. It had a flow rate or a RPM of 15,400 RPM per minute, and had a rating of 3,000 horsepower that it would generate. So those were two of the things that started the whole process of ignition. So the fuel would flow to the low pressure pumps, and then whenever everything else on the engine was ready to fire, then those valves would open, and that fuel would flow respectively through that low pressure pump and feed the high pressure pump. There was no ignition. We had a pre-burner mounted inside that casing that was basically an igniter system to ignite those gases when they came in to that system. So we had a high pressure oxidizer pump and a high pressure fuel pump. So let me give you some ideas of what they showed. The high pressure oxidizer pump had a flow rate of 1,100 pounds of propellant per second. Per second. The high pressure pump spun at 28,000 revolutions per minute, had an internal pressure of 5,200 psi at a rating of 29,000 horsepower. That's just on the LOX, or the liquid oxygen side. On the fuel side, the high pressure pump had an igniter inside it that it would ignite the hydrogen gas that was coming in from the low pressure pumps. So it'd come in there. The power on the high pressure pump was 35,000 revolutions per minute, an internal pressure of 6,200 psi, and a horsepower rating of 63,800 horsepower. So they were some more piece of machineries.
Enormous amount of power.
Right. If you say, well, how big is a turbo pump? A low pressure pump is about so big. Both of them, liquid oxygen, liquid hydrogen. Whenever you went to the high pressure pumps, the oxidizer pump was about so big around and so tall. Whenever you went to the hydrogen pump, that was the most challenging component I think that we had, was the hydrogen pump. It would give you a visual. It would fit, I would say, down in a 55-gallon drum, if you know what a 55-gallon drum is. About so big around and so deep. So it's just amazing the power that they got out of that. Now, we did have one other ignition source, and that was right over the main combustion chamber. So let me describe it briefly. We had what we called a strong back for how this engine went together. So in this strong back, while we had the high pressure pump on one side, another high pressure pump on the opposite side. In the middle of that was the main combustion chamber. So the fuel would flow through the low pressure pumps into the high pressure pumps and then feed through this strong back, huge piece of metal into a main combustion chamber that had 600 individual elements, and it had an ignition source up in the top of that. So we had 3 ignition sources that all occurred simultaneously at the same instant. 2 igniters in each of those pre-burners and at that main combustion chamber. So then the gases would flow, and then it would go through this main combustion chamber that had 600 elements in it, and that's where the gases got mixed, and then from there it went right out into the nozzles. So it was a very complex. It's hard for me to describe to you the difficulties that we experienced with that. Let me just take the high pressure fuel pump, because it was our most challenging of all of them, but maybe it'll give you some idea. In that pump, when you got the ignition to ignite through the pre-burner, those gases that were coming in from the low pressure pump and feeding into that high pressure pump, once you got that ignition, it had 2 turbines inside the top portion of that high pressure pump. Those 2 turbines had, obviously it was circular on a common shaft, and we had turbine blades out that were inserted into that flow path. And those turbine blades were about as big as that first joint on your thumb. They were concave by design, and they were spinning at how many thousand RPM? 35,000 RPM. So they were really flying. So we had difficulties in being able to anchor those turbine blades into its wheel or its disc. We had cracks that would occur in that turbine blade surface. So that all of that we learned through testing. So that's when one of those blades comes loose at that, or if it fractures and it comes loose, you've immediately got a fire and you destroy that high pressure pump. So then, how many months did it take to build it? That's where you got to have many of them in the supply line, in the shop area. That's why so many people were in the shop environment. So that just gives you a little bit of an idea of what we had there. Well, it was all computerized.
Okay.
So we did have a computer. We called it a controller that was mounted right on the side of the engine. And I'm not an electronics person, but I can tell you from the time that from that engine start to the time of the shutdown, that controller or that computer was in control, and it was 50 times per second. It was making its round of checking all the health of all of the hardware that was inside that big engine complex. Whenever you start a test, you start out with fraction of a second. You just want to burp, just a very quick burp to see, did wheels start spinning like they were supposed to spin? Because whenever they start spinning at those very high RPMs, you get some centrifugal force growth of that, okay? So then now you're talking about things spinning very high against a stationary eye here, and if this wheel starts growing a little bit because of the centrifugal force, now you've got metal against metal, which creates a spark, which means you've got a fire. So it was all about not only the integrity of the hardware itself, but of all of the clearances that existed inside all of this rotating machinery, which was so critical. So again, you go back and you do a very short initial ignition test, and then you say, okay, next test you go to a little longer. You might do 1 second. Another, if that's good, then you may go to another second or two until you just gradually build that foundation of data and build your confidence that, hey, we're going to be okay. So testing is so horribly important for this engine, any rocket engine, really, and particularly when you put a man on that rocket. And I will say that Rocketdyne made every engine that man has ridden on into space.
Interesting. That's
So,
interesting.
so in that booster stage, it's always been Rocketdyne engine. So. Well, while I was not heavily involved with the Apollo program, I was able to take my family to the Cape for the launch of Apollo 11. And so I took 3 kids down there. And so we did, we parked out in some remote parking lot, put blankets out on the ground. Kids slept through the rest of the night, and I woke them up the next morning to watch the launch. So I would say that probably is the highlight.
That's an amazing
Yeah.
family memory.
Right.
That's amazing.
But I will tell you also, whenever I was able to see the Space Shuttle launch, knowing what I knew about it and knowing that there's greater than 4,000 piece parts in every engine, every one of them has to perform exactly right. And to know that there's 3 engines up there, there's somewhere back in his history, I was fortunate enough to be a part of that. That was very satisfying. And then you fast forward to now we've got the SLS program. I'm not sure I'll still be around at that point in time, but if I'm still around, well, I sure want to be able to witness that launch as well. Well, I'm on a board here at the Space and Rocket Center, so I do get to feel the heartbeat of still what's going on, certainly within Marshall Space Flight Center and here at the Space and Rocket Center, and a lot of the talks between Washington and the politicians and the space programs. I think it's a pretty tight program to be back on the moon in 4 years, but I believe we can do it. And then for SLS launch, that's yet to be proven because we've not even tested our first SLS yet. So that Space Launch System is not far away. We do have an upgraded SSME that's going to power the SLS program to Mars.
Okay.
And as a launch. So I think that again speaks for the integrity of Rocketdyne and the engineering, unbelievable engineering that has gone into that machine to be able now to be the candidate, the engine of choice for the booster stage going to Mars. That's very rewarding.